Hi, this is Tzvi Rosen. Today we'll be covering Chapter 6 in the T.M. MacDonald, which talks about chain conditions. We'll begin with chain conditions on modules, then move on to properties of these modules that satisfy chain conditions called Noetherian and Artinian modules. Then we'll look at the special case of Noetherian and Artinian rings, and finally discuss what it means for a module to have a composition series. Okay, let's get started. The first condition we'll define in some generality is the ACC, or ascending chain condition. Okay, ascending chain condition, or ACC. And what it means is as follows. So if you have a poset, partially ordered set sigma, and our partial order is given by less than or equal to, and obviously whatever symbol it is fine. Then the ascending chain condition is as follows. So sigma satisfies the ACC if for any sequence x1 less than or equal to x2 less than or equal to x3, etc., the sequence is eventually stationary which means that there exists some index n such that xn is equal to xn plus 1, etc. So everything after xn in the list is equal to xn. Okay, you might also say the sequence stabilizes. All right, so this is called the ascending chain condition. And this is one condition. An equivalent condition is that this is called the maximal condition. Okay, which says that any subset of sigma, a non-empty subset, let's make sure that's clear, non-empty subset, has a maximal element. Okay, so you might say the ascending chain condition seems to be a bit more specific, like it's specifically related to these chains, but these two conditions are actually equivalent. And let's show that to be the case. So ACC implies maximal. So we can prove the contrapositive. So not maximal implies not ACC. Not ACC. So we prove the contrapositive. So if a subset of sigma is not does not have the maximal property, meaning that there's no maximal element in that subset, then we can choose one element after another, which is greater than the previous element we chose, but which is not itself maximal. So inductively build x1, you can just choose that arbitrarily. But then since x1 is not maximal, you'll have some x2 greater than it. But that also is not maximal, so you'll have x3 greater than that, etc. But then if this satisfied the ACC condition, the ascending chain condition, we would have that this stabilizes. Since this does not stabilize, since this is not stationary, I'll say, ACC fails. Okay, so that's one direction. The other direction, if you have the maximal condition, that implies the ACC. This way is a bit easier. So take the set of elements xi, I equals 1, 2, etc. This has to contain a maximal element. So the maximal element must be in the set, so it'll be xn. But then, since this is a sequence which is ordered by this partial ordering, this will be equal to everything after it. Okay, since xn is greater than or equal to xk for k greater than n, but we also have that xn is less than or equal to xk by the setup. This implies that xn equals xk for k greater than or equal to n. Okay, and that gives us the ascending chain condition. Okay, nice. By the same token, just flipping everything around, you'll have the DCC defined. This is the descending chain condition. And here, so this will be the DCC. This means that if you have the same situation where you have sigma and the relation less than or equal to is a poset, and we have some sequence x1 greater than or equal to x2 greater than or equal to x3, etc. This is stationary. i.e., there exists n such that xn equals xn plus 1, etc. Okay, and just as in the other case we had the ascending chain condition equivalent to the maximal condition, we have the descending chain condition is equivalent to the minimal condition. Which says that any subset, any non-empty subset, has a minimal element. Okay. And the proof of that these are equivalent is essentially the same as the proof for the ACC and the maximal condition. And when we have that, when we have a set of modules, when we have a module whose set of submodules is ordered by inclusion, okay, so if we have sigma equals submodules of M and less than or equal to is given by the inclusion, by the subset relation, then a module satisfying the ACC is called a Noetherian module. So this is so if sigma satisfies the ACC, that then we call the module M Noetherian. Okay, and obviously this is named after Emmy Noether, the great algebraist we've mentioned in the past. And if it satisfies the DCC, then we say that M is Artinian, named after Emil Artin, a great algebraist who studied modules satisfying this descending chain condition, in addition to other great swaths of algebra. Okay. So again, we have Noetherian modules whose submodules satisfy the ascending chain condition, and Artinian modules whose submodules satisfy the descending chain condition. Okay, so let's mention some modules which satisfy the ascending and descending chain conditions. So this would mean that the modules are Noetherian and Artinian. A simple example would just be any finite abelian group. So you could pick, for instance, Z mod 8Z. Okay. And obviously this is a Z module, so we're still talking about modules over a ring. Any finite abelian group is a Z module. Okay, and these Z modules, since they're finite, they only have finitely many submodules, so the chain conditions are easily satisfied, as well as the equivalent minimal and maximal conditions. Okay, by the same token, even if it's not a finite group or a finite module, but it has only finitely many submodules, you'll also find that it's Noetherian and Artinian. So for example, if you take a field, so a field K, for example, the rationals, this has, the only submodules are the whole field and the zero submodule. Okay, and I guess we should specify what ring we're talking about, the only Q submodules. So that means that any chain is just going to involve those two. So of course it'll be stationary. Chain conditions easily satisfied. Next, we'll discuss some examples where the ascending chain condition is satisfied, but the descending chain condition is not satisfied. In other words, these are modules which are Noetherian, but not Artinian. And for those, we can look at the integers. Okay, and an example of a descending chain, which is infinite, would be 2 contains 4 contains 8, etc. 2 to the n. So this chain of modules is getting small. This chain of submodules of Z, which are ideals of Z, are getting smaller and smaller. But at no point does it stabilize. The sequence is not stationary. On the other hand, given some ideal n inside of Z, so and every submodule of Z can be expressed in this way. It's the principal ideal domain. This will be written as P1 to the R1 times Pn, or Pk to the Rk. So there are only so many prime factors. So if you're going to make this bigger, you're going to have to shed some of these prime factors, and that process has to eventually stabilize. Okay, so this contained in any sequence must stabilize. Okay, by the same token, whenever we have Z, we always seem to have the polynomial ring in one variable over a field. So K adjoin X for K of field. not going great. K adjoin X for K a field. So similarly, we can find a descending chain. So descending would be just any irreducible polynomial. So you could, it's as simple as x, let's say. And then that contains x squared, which contains all the subsequent ideals generated by powers of x. Okay, so this doesn't stabilize, or it's not stationary. Okay, on the other hand, if you want to start any ascending chain, okay, your first ideal will be some irreducible polynomial, or some product of irreducible polynomials. This is equal to f1 to the k1, fr to the kr, where the fi are irreducible. So any ideals containing this has to be generated by some factor of this polynomial, and so you only have finitely many factors to choose from. So eventually the sequence is going to stabilize. Okay. DCC but not ACC. This is we're looking for Artinian module, which is not Noetherian. And this is actually tricky. There's a nice example in Etienne MacDonald, and if there hadn't been, I would have had to work harder to construct one. It goes as follows. So let's say we have, we're looking at G equals Q mod Z. Okay. And then we're looking at the subgroups where you take everything of a specific prime order or prime power order. So if you take so H0 to be the elements of order, let's be concrete and say p equals 2. So this will be order 2 to the 0, which is 1. Then H1 will be elements of order 2 to the 1. So that's elements of order 2. So here you're thinking of the 0 element. That's the only element of order 1. Here it's 0 and half. And obviously we're talking about these as representatives of the elements in the quotient group. Okay, so H2 is the same, but for 2 squared equal, so same, but with 2 squared equals 4. So anything of order 4. So we're looking at the elements 0, a quarter, a half, and 3/4. Okay. So this is an ascending chain of modules. And we can take the kind of the union of all of these. So we'll define H to be the subgroup of G with where each of the elements has a representative of the form n over 2 to the k. Okay, so k greater than or equal to 0. Okay. So H given by this. All right, so clearly we have this ascending chain. And this is not going to terminate. This is not going to stabilize because it's getting, each time you pick up more and more fractions that are in the corresponding submodule of H. On the other hand, the descending chain condition is satisfied. So this is an ascending chain which does not stabilize, so not stationary. If you wanted to find a descending chain which didn't stabilize, well, we'd have to start with a submodule, and that would look like one of these, right? Because it's going to be generated by a fraction with some denominator. So let's say you start with hn, then there's only so many subgroups that are strictly contained in this, right? So you're going to be stuck with this n is eventually going to tick down to 0, and then it's going to stabilize. Okay. So for that reason, this is an Artinian module, which is not Noetherian. But it's hard to construct these examples, and we'll see that Artinian rings are also Noetherian. So there's an asymmetry there. But you do have Artinian modules, which are not Noetherian. Okay, now let's look at a couple of examples which satisfy neither the ascending chain condition or descending chain condition. So these modules are not Noetherian and not Artinian. And one of those would be the polynomial ring in infinitely many variables for K a field. And the reason that this is neither Artinian nor Noetherian is we have x1 contained in x1, x2. Okay, these are ideals contained, etc. The ideal x1 through xn, and this is not a stationary chain. Okay, so this is the ascending version. As for the descending, here you can just use the same idea as for a normal polynomial ring. x1 contains x1 squared contains x1 cubed. Okay, that one's not hard. Second example is the algebraic integers, which are the integral closure of z in q bar in the algebraic completion of the algebraic closure of the rationals. Okay, and we're thinking of z bar as a module over itself. Okay, then we have the following ascending chain. We can start with the ideal generated by the square root of 2. This is contained, so this is clearly an algebraic integer, since it solves the monic polynomial x squared minus 2. But this is contained in the submodule generated by the fourth root of 2, which is contained in submodule generated by the 2 to the kth root of 2. And this never stabilizes. Okay, so this is not a stationary chain. Similarly, for the descending chain condition, we have that z is a submodule of z bar, so we can easily just get 2 contains 4 contains 8, etc., 2 to the k. That part is easy. Okay, so these are examples of modules that are neither Noetherian nor Artinian. Okay, and now we can move forward to prove some properties of Noetherian and Artinian modules. We start with a result relating the ascending chain condition and finite generation of submodules. So the theorem is as follows. Let M be a module then M is Noetherian if and only if every submodule is finitely generated. Okay, and let's prove this theorem. So going one way, we can use the contrapositive. Suppose we have some submodule which is not finitely generated. So do the contrapositive. Suppose n, there exists a submodule n in M not finitely generated, then its list of generators, if you take sublists and see the submodule they generate, that will be an ascending chain of submodules which will not be stationary. Okay, so take a list x1, x2, etc., elements of n such that xi is not generated by x1 through xi minus 1. Okay, and the assertion that that n is not finitely generated means this you have to be able to find such elements. Okay, then the chain x1, x1, x2, etc. is not stationary, so M can't be Noetherian. Okay, in the other direction, so if we're saying that every submodule is finitely generated, okay, then we want to, or we want to show that the ascending chain condition is satisfied. So consider, this is the other direction. Consider N1 contained in N2, contained in N3, etc. So we can think of, we can basically take the direct sum of all of these modules. Okay, so let n be equal to the direct sum of all of the ni. So this is a submodule of let's make it the union. Of all of the ni. And this has to be a submodule. It's not hard to check that. So that means it's finitely generated. But if you have finite generation, each of these xi's has to be in some ni. So each xi is in ni for some I. So take the highest index for each of the m elements. Then the union of all of these submodules, by virtue of being generated by these m elements. So take the highest index. Let's call it capital M. Or no, we're starting with a capital M. So let's take the highest index to be capital K. Okay. So then n is contained in nk by virtue of all the elements being in nk. But we know that nk is contained in n because n is the union of all of the submodules. This implies that n is equal to nk, which means that nk plus 1 equals nk, etc. So the chain is stationary. Great. Okay, so we have finite generation of submodules if and only if the module is Noetherian. Okay, let's look at exact sequences. So here we have the following theorem. So let 0 to m prime to m double prime to 0 be an exact sequence of modules. Then we have two results, which are just mirror images of each other. M is Noetherian if and only if m prime and m double prime are Noetherian. And by the same token, M is Artinian if and only if m prime and m double prime are Artinian. Okay, so this guy is equivalent to these two guys, being whichever of those two properties. Okay. So let's prove the Artinian case. You can check the Noetherian case in the text of T. M. MacDonald. So we want to show that M is Artinian if and only if m prime and m double prime are Artinian. So let's prove this direction first. So assume that M is Artinian. We want to check that m double prime and m prime are also Artinian. So let n1, n2, etc. be a chain of submodules of m prime. Okay. Then by applying the map to M, these map to a chain. Oh, I'm sorry. We're talking Artinian still. So we have to be a descending chain. So this looks like this. So these map to a chain in M. Okay, and by the fact that M is Artinian, so M is Artinian, so that means that the chain is stationary. That n k plus 1 is equal to nk, or rather let's call it nk is equal to nn for all k greater than n. But we know that the map into M, sorry, maybe let's put a bar to indicate that it's the image of the map. Okay, so the pre-image, and let's give these maps names. So this will be the injection into M, and then these will be the projection onto M double prime. Okay, so now I can just write it like this. So I of nk is equal to I of nn for all k greater than n, but since I is injective, that means that nk is equal to nn for all k greater than n, which means that the descending chain condition holds for m prime. Okay, in terms of m double prime, consider a chain n1, contains n2, etc. in m double prime, then we can consider the preimage under pi of those submodules. So pi inverse n1 contains pi inverse n2, etc. is a chain in M. Okay. So obviously this is stationary because M is Artinian. Implies eventually preimage of nk is equal to preimage of nn. Okay, obviously different k and n, fine. For all k greater than n. But here, at this point, it's a little trickier, so because we don't have injectivity of pi. So how do we show that this implies that the chain stabilizes in M double prime? So suppose we have, let's take a new page. But since pi is surjective, if the two pre-images of the modules are equal, that means that the modules themselves are equal. Because if you had something that was in one that wasn't in the other, then you would also have the preimage, so y. So if x is in nk and x is not in nn, then the preimage of x would have to be in the preimage of nk, which would mean that it's in the preimage of nn. But that would mean that x itself would have to be in nn. Okay, because the preimage of x will map uniquely to x. So okay, so that completes the proof that if M is Artinian, M prime and M double prime are Artinian. So what about in the other direction? So if M prime and if M prime and M double prime are Artinian, how do you show that M itself is Artinian? So let's take a chain of submodules n1 containing n2, etc. in M. Okay. So if we look at the preimage of under I, so I inverse of n1 containing I inverse of n2, etc. This is stationary by the fact that M prime is Artinian. Okay, so this implies that I inverse of nk is equal to I inverse of nn for all k greater than n. Okay, and how about the image of the chain? So pi of n1 contains pi of n2, etc. is also stationary. Okay, which means that pi of nk is equal to pi of nn for sufficiently large k, for k greater than n. Okay, and I'm using the same n because you just take whichever is bigger. Okay. So what do we have as a result of these two properties, of the fact that m prime and m double prime are Artinian? Well, suppose we had that, for instance, nn plus 1 is not equal to nn. Okay. So then that would imply that there exists x in nn, okay, because we're a decreasing chain again, such that x is not in nn plus 1. But since pi of x is stationary, pi of x will be, but since the chain of the pi's is stationary, so pi of x is going to be in pi of n plus 1. In particular, you can write it as the sum of some, or really just the image of some element, since pi is surjective, so equals pi of x n plus 1. Okay. But if pi of x equals pi of x n plus 1, that means that pi of x minus xn plus 1 is equal to 0, okay? But x is not in nn plus 1, so this is an element of nn, which is not an element of nn plus 1. Okay, so x minus xn plus 1 is not in nn plus 1. Okay, and its image is 0. But we know that the kernel of the map pi is equal to the image of the map I. So this means that there exists y in m prime such that pi of y, such that I of y equals x minus xn plus 1. And since x minus xn plus 1 is in nn, implies that y is in I inverse of nn, which means that y is in I inverse of nn plus 1, which is a contradiction. Because then x minus xn plus 1 will be in nn plus 1, even though x is not in n plus 1. Okay. So, a little bit convoluted, but the idea is you chase things backwards and forwards, and you eventually find the contradiction you're looking for to show that M itself must have the chain stabilizing, must satisfy the descending chain condition. Okay. Corollary of this is that if you have a sequence, if you have a direct sum of Artinian modules or Noetherian modules, so let M1 through Mn be Noetherian modules, and the same obviously holds for Artinian. Their direct sum, mi, I equals 1 to n, is also Noetherian. Okay, and you can just construct exact sequences that using the mi's with the direct sum in the center building it up inductively so that you can just prove it from the exact sequence result. Same for Artinian. Okay. Now, when we talk about Noetherian or Artinian rings, so far we've only been talking about modules. If R is a Noetherian or an Artinian module, when considered as an R module, so it's a module over itself, then we say it's a Noetherian or Artinian ring. Okay, and when we think about what are the R submodules of R, well, those are the ideals. So this means that we can talk about that R satisfies the ideals of R satisfy the ACC, or in the case of Artinian rings, we're looking at the DCC. Okay, so that's Noetherian and Artinian rings. Now we'll think about finitely generated A modules. If A is an Artinian ring or a Noetherian ring, and M is a finitely generated A module, then M is Noetherian or Artinian. In terms of quotients, if you have, let A be a Noetherian or Artinian ring, then so is A mod P for P an ideal. This isn't hard to prove. Basically, the ideals of a quotient ring are in bijection with the ideals of A containing P. Okay, so if you have the chain condition satisfied for A, then passing to the quotient will also be satisfied for A mod P. Okay. Now we'll define a composition series. So let M be a module. Take 0 equal to M0, proper submodule of M1 up to Mn, and this is our M, such that this chain is maximal. In other words, no other submodules can be inserted into the chain. No other submodules can be inserted to lengthen the chain. This is called a composition series of M. Okay, composition series. Let's underline it. Okay. So we have a theorem that composition series have fixed length. So if you have one composition series of length n, then every composition series has length n. So M0 contained in up to Mn a composition series. Okay, this is a maximal chain of submodules. Every other composition series also has length n. Okay. And the proof of this involves, so the idea of proof take any submodule, a proper submodule, n in M, so then you should be able to find that given a composition series of n, any composition series of n or rather, so if you intersect the mi's with n, so mi intersect n gives a composition series of n, okay, because after you discard any inclusions that are not proper, after discarding repeats, okay, because these intersections, you're always going to have the quotient of mi plus 1 intersect n by mi intersect n either being the 0 module or the whole module, because it's supposed to be a simple module. So this will have smaller length than m, okay, and let's call this the length of m. So since any submodule has smaller length than m, there's no way that you're going to get a longer chain reaching to m, because if you have, if it takes n plus 1 to get up to some proper submodule, then, or if it takes n to get up to a proper submodule, then you've just contradicted the idea that any submodule has this smaller length. So that's the idea of the proof, that the length of the module, i.e. the length of this composition series, is fixed. Okay. So a module has a composition series if and only if it satisfies both chain conditions. This is not hard to see. I mean, you just basically write it down. So if you take m, so you have 0, which is equal to m0 contained in m1 up to mn, and this is equal to m. So we want to show that this is true if and only if m is Noetherian and Artinian, Okay, well, in one direction, it's going to be pretty easy. So going this way, if you have any chain of submodules, so let's say an ascending chain, so mi prime or m1 prime, m2 prime, etc., going up. So assuming all of these inclusions are proper, and if they're not, then you can just throw them away. This is a so throwing away repeats gives a composition series, but we know that has fixed length. Composition series for whatever the max submodule is, for the highest unique term, but this has bounded length. Going the other direction, so we have our module, it's Noetherian and Artinian. So because it's Noetherian, it has the maximal property. So let's take the maximal proper submodule of M. So we have M equals M naught. Okay, so take M1 to be the maximal proper submodule of M, and then continue inductively. Okay. So this gives a chain M equals M0, which contains M1, which contains M2. And by maximality of each of those, that's a maximal chain. This is a maximal chain. But by the descending chain condition, which is satisfied by Artinian modules, this stabilizes. Okay, and that gives a composition series. Okay. Finally, I'd like to discuss vector spaces and chain conditions. So if you have a vector space over field K, so let K be a field, and V a K vector space, then the following are equivalent. So first of all, V has finite dimension as a K vector space. V has finite length as a K module. V satisfies the ascending chain condition, and it satisfies the descending chain condition. Okay, so the proof of this is not too bad. 1 is equivalent to 2 really just by unpacking the definitions. Okay, so the only kind of new point here is that one of the ascending chain condition or the descending chain condition proves that it's finite dimensional, but I mean, you can look at the contrapositive. So suppose V has infinite dimension. Then it's not hard to take to construct an ascending chain, a non-stationary ascending chain, and same for a descending chain. Okay, so for instance, 0 contained in, one of the basis elements, the span of one of the basis elements, contained in the span of two of the basis elements, etc. And by the same token, you can just take out, V, the orthogonal complement to the span of E1, orthogonal complement to the span of E1, E2, etc. This is a descending chain. And neither of these are stationary in that case. So that proves that either the ascending chain condition or the descending chain condition implies that V has finite dimension. Okay, and the other way is trivial. Okay, and the final result in the section is that if we have the zero ideal equal to the product of some finite collection of maximal ideals, okay, suppose A is a ring such that Mi in A is maximal, and the zero ideal is equal to a product of those maximal ideals, then A is Noetherian if and only if it's Artinian. And the key here is to use the fact that it's equivalent for a vector space to be Artinian or Noetherian. It's as follows, so proof. So we have the following chain. So A contains M1, contains M1, M2, etc., down to M1 through Mn minus 1 contains 0. So this is a maximal chain. This is a maximal chain of ideals. And if we look at the quotient of each term, of each consecutive pairs of terms, so A mod M1, M1 mod M1, M2, this is just equal to M1 times A mod M2, okay, etc. These are all fields, or vector spaces over fields. So each vector space is Artinian if and only if Noetherian by the last result we just proved. So that means that each factor is Artinian if and only if it's Noetherian. But then that means that the module that you build by putting them one after the other, which is just the ring, so that the ring constructed from those vector spaces is also Noetherian if and only if Artinian. And I am eliding some of the details, but the key here is that you can use exact sequences to build the ring inductively. Okay. And I'll end the lecture there. Thank you so much for your attention, and look forward to seeing you next time.